So have we got everybody here?
Possibly.
Youngster's not here.
Rob and Nick. Yeah.
So
No,
do you want me to
No,
start?
you can start. Yeah.
Okay. Let me just share my screen.
Yep, that's working.
That's working. Okay, can we see all that?
Yep.
Okay. I had a quick look through what Mariana covered last week, and I think she spent most of the time on the drive pulleys. Is that right?
And she said she was going to do the non-drives this time.
Yep. So we'll do the non-drives. What I would like to do, I just want to spend a couple of minutes on one additional thing on the drives that you might find interesting, and that's I think is useful with lagging select, and it actually has some relevance to the non-drive. So if you can just bear with me for a few minutes while I'll just run through this example that you can see on the screen. You can see all of the conveyor data that's been put in here, and I'm just going to very quickly run through. There's about 8 different laggings, or actually 4 different laggings, but each one in 2 different thicknesses, and then at the end we'll just do a comparison, because the comparison shows one of the really useful things for using lagging select that benefits both drive and non-drive. So this is 12 mil diamond rubber. You can see the graph there. We go to 25 mil. Graph doesn't change much. You can see down the bottom here there's a little bit of slippage. So this is all on the same conveyor, and we're just analysing the different laggings. Then we look at 12 mil diamond ceramic, and I'm not going to go through the individual graphs because it's really the summary at the end that's important. Then 25 mil, that just reduces the amount of slip because it's a more flexible lagging. 20% ceramic, 12 mil, and then 25 mil. 38% ceramic in 12 mil and 25 mil. And then the last one is the 80% ceramic in 12 mil and 25 mil. And then this next slide, which is the main one that I wanted to look at. So this is just a summary of all of those different analyses that we just looked at. And this is one of the things you can do with lagging select. So across the top here, we have the different laggings. So the diamond 12 mil, 25 mil, the diamond ceramic 12 and 25, the 20% ceramic 12 and 25, and so on. You can see the ceramic coverage across here. Can you guys see the cursor?
Yes, we can.
You can see the cursor? Okay.
It's tiny.
And then, okay, well, I can maybe change that. What can I do here? Laser pointer. I think there. Can you see that?
Yep.
So here are the summaries of the results. So you've got the traction or slippage, and you can see the slippage ranges from 18%, 9%, etc. There's only one example that has 0%. So there's only one example with no slippage. And then down here we have all the fatigue results. So we have I think Mariana would have gone through how lagging select looks at the fatigue at different positions in the lagging. She covered that last week.
Yep, definitely.
So again, you've got the summary of the results of that in these 4 lines: contact face shear stress, tread root shear stress, pulley shell shear, tread root shear stress, and the tile bond shear stress. This one down the bottom, this is really really useful, this maximum shear stress. So I mean, in this particular example, there's only one lagging that has no slip and falls within the fatigue envelope. So the decision on which lagging to choose is pretty straightforward. However, if you were doing a bunch of analyses and you had more than one lagging that had no slip and satisfied all the fatigue requirements, the thing to look at is this maximum shear stress, because the lower the shear stress between the lagging and the belt, the kinder the operation is to the belt and the belt splices. And we're going to look in a minute at bend pulleys in contact with the dirty side of the belt, and in particular high tension bend pulleys. And we're going to look at the way that both the lagging and the belt get damaged and how they actually damage each other. So when you're actually selecting the lagging to go on a pulley, if you can choose the one that creates the smallest amount of shear stress and at the same time satisfies the slippage requirements and the fatigue requirements, then you'll have it'll be a better result for the both the lagging and the belt. I've just got to jump out of here for a minute. Now I've got to get to slide number. Sorry, got to go back to sharing again. Okay, does that come up again?
Yep.
Okay. So non-drives, we're going to look at the main challenges, and we're going to focus on the pulleys that are in contact with the dirty side of the belt, because these are the most demanding ones in terms of what happens with the lagging. Sorry, just let me turn this off. So here we're looking at a diagram of what actually happens when you've got the belt contact surface wearing, and this graph is shear stress up the vertical axis, and then you've got the face width across the horizontal axis. And what you get is you get this localized shear, these peaks that line up with the edge of the wear profile. And this is caused because as the belt cover wears, the cords that are in this area are traveling a different distance to the cords that are out on the edge. And that creates these localized shear stresses. So you've got these points of high shear, and then in the center you've got point of low shear. And we're going to have a look at what that does to the lagging. I don't know if you guys have you seen pulleys like this?
Yep.
Yep. Okay. Common problem, particularly with bend pulleys and high tension bend pulleys, where you get this wear pattern through the center.
I think the mechanism, David, on that is, if I just help me, I understand that the belt itself gets worn, so therefore you get that profile where when it comes over onto the dirty side, you end up with a different diameter of the I'll say steel cords across, so you have lateral movement or longitudinal movement. Is that the main driver for that kind of problem?
Yeah, well, you've actually described it in a nutshell. There's two problems. One's the wear, and the second is the damage that it can do to the steel cords in the belt.
Yeah.
So what you've described is you get torsional slippage because of the cords in the center are going around a different diameter,
yeah.
and that accelerates the wear on the lagging. And we can actually predict that. Right at the end, I'll show you on the lagging select how we can tell whether the conditions are going to cause the lagging to fail or whether it's going to be okay. The second thing is this wear profile can actually damage the cords in the splices and also in the belt. Just go through that. So yeah, this is just the diagram showing that, like here, the belt has worn, and that's then causing corresponding wear in the lagging. And if we talk about lagging gauge differential, is basically the difference in the lagging thickness from when it was new. So like, say, right in the center of the lagging, when the lagging's brand new, let's say it's 20 mil. If you get 5 mil of wear, so in the center it's gone down to 15 mil, we would say the lagging gauge differential is 5 mil. We've lost 5 mil of the lagging thickness. And then, so this graph is basically showing if you've got these different gauge differentials across the horizontal axis, that creates a belt speed differential. So for, say, 10 mil difference in thickness of lagging, you've got just over a 1% speed difference in the center, and then it's that sliding of the belt in the center over the lagging that accelerates the wear. And then obviously when you get to 20 mil of gauge differential, you know, you're looking at between 2 and 2.5% speed difference. And this shows up on your ceramic lagging. You know, you get this very neat area in the center of the pulley that gets damaged. On your rubber lagging, again, you'll see this wear in the center. This photo on the right, this photo here, a lot of people, when they do rubber lagging on bend pulleys, they use calendared rubber, which is basically multiple layers. When rubber lagging is exposed to this type of shear, it's very common for those rubber layers to delaminate, which again reduces the life. It's much better if you can have molded rubber on these pulleys, because it won't delaminate. So this is an interesting thing, interesting graph. This one at the top is the conveyor belt wear in months from new. So over here where my laser pointer is, if you imagine this is 0, so the belt's brand new, and we're going across 18 months, 30 months, 38, 42, 47 months. Up on the vertical axis, we've got the lagging life performance. So you have a brand new system, you've got new belt, you've got new lagging. This is the first lagging that goes on. And we're talking again here about the bend pulleys in contact with the dirty side of the belt. So the new lagging, it's working without any localized shear until the belt cover starts to wear, and let's say arbitrarily it lasts 18 months. So now the lagging has to be replied, and you put exactly the same lagging on, same manufacturer, same application method, etc. And it only lasts, this time, the second time, it only lasts 12 months. And the reason it only lasts 12 months is that now this second lot of lagging, it's actually dealing with a worn belt. So you've got the slippage from the torsional shear. Problem is, a lot of site maintenance people look at it and they think, no, this is a problem with the lagging. The lagging's a lower quality, or it hasn't been put on properly. This situation continues. Then you put your third lot of lagging on, and again, it won't last as long as either the second or the first. It's just a continuing downward, a continuing reduction in service life as the amount of belt wear or the gauge differential on the lagging increases. This graph here at the bottom, this is actually this is real actual maintenance data from a mine we did some work with in Chile, where they were logging. This is the thickness on this vertical axis. This is the lagging thickness. Across the bottom, they were graphing the millions of tons of ore that they'd processed. And they were using this to determine when they would initiate a lagging change. So this orange line, they were allowing, when they got to 6 mil of remaining lagging thickness in the center, that was when they were going to make the change, because they didn't want to damage the pulley shell. The reason I'm showing this is you're going to see that when you start to get into this very severe decline in thickness, because you're getting a lot of wear, you can be doing a lot of other damage to the belt. Not so much the lagging, but you can be doing a lot of other damage to the belt, which we'll look at in a minute. So I just want to explain chord plane differential. So this is what we say is the distance between the bottom of the wear in the belt and the bottom of the wear in the pulley lagging. If we were to draw a horizontal line, actually, if we were to draw a horizontal line across here, the chord plane differential is the belt wear. So this here added to the lagging wear. So what happens? This picture at the top is actually an X-ray. We were introduced to some work that was done at a very large mine in Peru, where 80% of their splices were not lasting anything like the 12 years they were supposed to. I think 80% of them were failing within 3 years. And so they brought in a firm of consultants, and they basically X-rayed every single splice in the belt. I think there was something like 32 splices. And a lot of the causes of the problems were breakage or damage to cords, which you can see here. Now, in a large majority of the cases, the damage and breakage to the cords lined up with the edge of this wear pattern. So the edge of the wear pattern where we know we have the high shear stresses, and I'm just going to show you what we think is causing that. That's just another one of the X-rays where you can see the cords. These are cords that have been dislodged. So this graph is basically a graph of the fracture strength or load stress for the steel cords in a belt on the vertical axis. And then across the horizontal axis is the number of cycles to fracture. So you have this region which is called the infinite life region, where you can have as many cycles as you like and the cords won't break. And there's a fatigue limit, which is around about the 50% of the total shear stress or strength of the cord. And from what I'm told, most steel cord belts are designed to be operating at around about 20% of the infinite life strength. So we've got basically 3 graphs here. The one on the bottom here is the cord tension on the vertical axis, and the cord position or cord number on the horizontal axis. And then across on this graph on the top is on the vertical axis is the wear, and then on the horizontal axis again is the cord number or cord location. This third graph, we've got what we call a stress multiplier. So it's a magnification of the stress that you get on the edge of the wear, and we measure it with the chord plane differential, so that the amount of that distance, which is the combination of the wear of the belt and the wear of the lagging, So when these particular graphs are when the belt is brand new, so there's no wear in the belt, and the lagging's brand new, there's no wear in the lagging either. And so here your stress multiplier is 1. So there's no magnification of the stress because there's no wear, no stress. So these graphs are where we have 10 millimeters of chord plane differential. So we have our little graph with the localized shear stress on the edges of the wear area. And the way we work out the stress multiplier is we take the top of these peaks, which is around about 21.8 kilonewtons, and we take the bottom of the center of the wear area where we have the least stress, which is 13.98, and it's the 21.8 over the 13.98. So we have a stress multiplier of 1.559. Or I've rounded it up here to 1.5 for 10 mil. If we then go to 20 mil, so this is 20 mil of chord plane differential. Again, the stress multiplier is the difference between the top of the peaks and the bottom of the trough. And here for 20 mil, we're getting a stress multiplier of just over 2. So basically, if we come back to our graph of infinite life, when you've got 20 millimeters of chord plane differential, we're getting up towards the transition between the infinite life region and the finite life region. Now, if you look at this graph here, which this is only measuring the lagging. There's no allowance in here for the belt wear. And let's say you assumed that the amount of wear in the belt was corresponding to the lagging. Basically, to get that 20 mil chord plane differential, we'd have 10 mil of lagging wear. We'd be out here somewhere, and a corresponding 10 mil of belt wear. You can see when the mine continues to operate that belt and the lagging wear increases and the belt wear is increasing at the same time, it's not going to take much before you've moved into the finite life region for the chords. And this is all theory, but that's what we think is causing the damage to the chords in the splices and the belt, where it lines up with the edge of the wear profile.
David, Sean and I were talking about this this week, and one of the things that Sean was talking to me about is coming into a transition on a head pulley, particularly, and that's not going to be a dirty side belt, but potentially it could be a drive head pulley. The transition itself, as it approaches the drive pulley, generally leaves a W-shaped tension stress field. It's not homogeneous. As the belt approaches the pulley, you don't have this nice even tension spread across the belt. You have a W shape, a bit like what you were showing before from the chord misalignment. You get a double peak. So has any of that been taken into account, that there'll be 2 points where the tensions will be higher and there'll be potentially 3 points where the tensions will be lower, coming around that drive pulley from a transition, or anywhere where there's a transition, even a tail, I suppose?
We've had a couple of cases where a lot of times we get asked to look at stuff, Kerry, where people are having problems in the field with unusual wear patterns, and what you've just described has come up a couple of times. And I'm not familiar with the exact details, because I normally look after the wear panels. Mariana looks after the lagging. She's a lot more familiar with it. But the answer is yes, we've seen that issue. And there has been analysis done using lagging select, but it's been referred back to Brad Lawson from CDI, who basically developed developed a lot of the algorithms in lagging select. So I can get you more information on that, but I can't.
Yeah.
I don't know it. I'm not au fait with it.
That sounds like a next round of education sessions by the sound of it.
Well, probably for something like that, the best thing. I mean, one of the things that we've done with Brad is when there's specific inquiries like that, we just set up a Teams meeting and we get him on, and if you've got specific details of the conveyor, we can plug it into, we can get him to do some analysis, and then he's the best one to bounce these sorts of questions off.
Yep.
And
he can see his point, because he would have surely considered this, I'd say.
We definitely have. I know of at least 2 instances where this has come up.
I just put a snip from the standard in the chat. That's what Kerry was referring to.
Sorry, chats. Yep.
Yeah, I think I wanted to reread it all again and just check. Because Kerry, I wasn't sure if you actually have a transition length that exceeds the amount that you calculate, whether or not the idea is that like if you do have that transition length, that differential tension across the belt is sort of back to zero by the time you get to that length, and it's maybe only there if people have shorter transition lengths than they should.
Yeah,
I think that's how the calcs work. I didn't sort of go back and read it all again. If anyone else has done that more recently remembers.
I think Stoney was in the conversation too. We've all seen on site, or at least I've seen it particularly on tail transitions, returning back to a single V. You see as it's approaching the V plow, supposed to be way past the transition, you've still got residual tension stress and that seagulling effect on the belt. So I'm not buying it, Sean. I still think there'd be some
still there. It's just the safety factors that they try to make the length so that the safety factor is not exceeded in that zone for the belt. Yeah.
Yeah, but then that's still affecting the performance of the lagging to some degree, because the tension profile will be different at those lines. So it'd be worth checking the sensitivity with Brad.
Yeah, I can see. I can tee up a time. We can have a separate session, and probably the thing, Kerry, if you've got a specific example that you can share, and if you've got photos, and if you can share the info that we need to plug into to lagging select, at least then Brad can do a bit of preparation, and then we can have a session and you can bounce ideas around.
Really stressed belts are probably not head drives, although the Tolgoi does have a head drive. And so that splice length, I think, is also a little bit compromised, and certainly the transition is. So that could be one that we could run. So what do you think of this one? Because that's brand new and it's only just been started up, and we haven't started nudging the safety factors on that belt yet because they haven't been running at design throughput. And that belt is right there on safety factor. So all of these things that you're indicating with the pulley wear may start to play in differential tension profile around the drive pulley if a belt is right on or perhaps I say a bit under the safety factor.
The reason that we raise this stuff, Kerry, is because when you understand the impact of the belt cover wear and the lagging wear and the other ramifications it creates, it sort of highlights the need to think about things like more abrasion resistant belt covers, better belt cleaning, changing the lagging more often, which obviously they don't like to do because those pulleys are usually big and difficult to change. But when you start looking at the consequences of not doing that, it can just change the decision making.
Yeah.
Okay.
Well, it's really interesting.
Okay, I'll go to the next one. Okay, so This is just two quick examples to show how you can use lagging select to determine whether or not on a high tension bend pulley you're going to end up with that severe damage in the center. So this particular example was on a conveyor in Brazil, ST4000, 66 kilonewtons, and 10 mil of top cover wear in the center of the graph. The top graph is the slippage graph, and you can see there is there's a lot of slippage in the center. But in this case, I think we were looking at ceramic lagging. Let me just check here. Yeah, double row, smooth ceramic. So even though there was some slippage there, because it was smooth ceramic, we didn't think that was going to create a major problem. And then down here in the fatigue side of things, this black line is the operational line, and you can see that it's below it's below the tread root fatigue limit, it's below the tile bond fatigue limit, it's below the lagging to shell bond limit. So basically what this is telling us is that this lagging can handle this service. Now, I should have mentioned earlier over here, this calculation's been done with 10 mil of belt cover wear. So in lagging select, when you enter all the data in, you can see up here T1 and T2 are the same, 662 kilonewtons. And we've put all the other information in that we put in for drive pulleys, but down here we have the ability to put in a nominal amount of belt wear. Now, if we kept increasing that 10 mil, eventually you'll get to a point where this operational line will come up and it'll exceed one of the fatigue limits, and that's telling you that at that point you can expect that you're going to start seeing some form of substantial damage. The next one I'm going to look at is this is actually a gearless drive conveyor in Peru. This particular conveyor was our first introduction to this problem many years ago, and it's got a 5 megawatt drive, and it has chronic problems with damage of the lagging. They've tried just about everything on this high tension bend pulley. Again, we've plugged all the info in. You can see up the top here, the T1 and T2 are the same. Down here, this has got 5 millimeters of belt wear. So it's not very much belt wear. And you can see here, this is the operational line for this pulley, and you can see it's exceeding the tread root shear stress, and it's exceeding the pulley shell shear stress as well. So what lagging select is telling us is that basically once you've got 5 mil of belt wear, you are going to see substantial damage to the lagging. This last section that Mariana had in the presentation was just a bit to do with build up on lagging, and you've got some photos here. Over here on the right, you've got direct bond ceramic lagging with build up. It's very prone to build up, and you can see on this particular pulley, it's created a line of damage in the belt that lines up with where the build-up is. The idea to try and prevent build-up is to have lagging that's flexible, that can move and can actually release the material, so that as it's compressed, it actually flexes and the material comes out, as opposed to a rigid lagging where it just builds up. This is just a little video to show how this works. So this is just this is a flexible rubber lagging just in a press, just to show the way that it's actually compresses and retracts each time it's loaded and unloaded. And then also the angle, you can see the angle of these grooves. It's designed to make it difficult for material to get trapped in there. So we basically promote, if you're trying to prevent buildup, you need to have a flexible lagging. Now that can be, you can have a flexible ceramic lagging. So for example, this particular lagging here, it's a rubber backed. This was in an application with a lot of carry back. You can see every tile's broken. You can even see there's material embedded, but at least you've got some degree of give in the rubber backing. From memory, this was 25mm thick lagging, whereas the direct bond, you've put something like direct bond lagging on there. It's rigid. It's there's no give. You get this point loading. If you have a rock like that between direct bond and a belt, you've got this very high localized force. The other thing with these pulleys in contact with the dirty side is something as simple as the shape of the grooves. You can see these grooves here on this pulley on the left. Nice wide grooves with a taper on them, as opposed to just a traditional diamond groove hand cutting, which tends to want to trap material. Sounds simple, but if you can get the lagging so that it sheds the material, you're less likely to damage the belt. And this is an interesting one. Some people put dimpled ceramic lagging on non-drives. We prefer to have plain ceramic. This is actually a copper mine in Peru, and they get this quite strange phenomenon. And if you see on where the cursor is, these are actually little pyramids. They treat the ore with sulfuric acid, and it wants to bond onto the ceramic tiles. If you then give it something like a dimpled tile to bond onto, you get these, we call them dragon's teeth. So I guess what we would recommend for a pulley like this is that it actually should be rubber lagging rather than ceramic. And just to follow up on what we talked about before, the change from when a belt and lagging are brand new to when the belt and the lagging are reaching the end of their service life, or well through the service life, and how the wear of both accelerates. That's pretty much all I've got. If there are any questions or anything you want to go through.
I've asked my questions. So
Yeah.
just going back to something you said about 2 or 3 minutes ago, I think the smooth ceramic on bend pulleys sounds like a really good idea. That's going to help some of those issues that you saw or showed us earlier, right? With particularly the cord belt wear on a dirty side, high tension bend. It's going to assist to stop any of that residual tension building up and overstressing cords. Is that what I'm thinking?
That's basically it. So if you look at so the iron ore industry in WA, they for a long time, Kerry, were running smooth direct bond ceramic on their non-drives, and they had the dimpled ceramic on their drives. And they ran into a lot of problems with the build-up on the smooth ceramic, and that was causing belt tracking problems. It was breaking, when it got bad, it was breaking cords.
Yeah.
And then they moved to hot cast polyurethane.
Right.
So you find now Rio Tinto and BHP and FMG have all got hot cast polyurethane in their specs. About 12 months ago, we started putting hot vulcanized smooth ceramic on the non-drives for Fortescue.
Yep.
And they've sort of been running that side by side with the hot cast polyurethane, and they're looking to see. We think the rubber back ceramic is going to give longer service life than the hot cast polyurethane, just by virtue of the greater wear resistance of the ceramic. It's still flexible, but the ceramic's got better wear resistance than the hot cast polyurethane, and so far it seems to be working pretty well.
And the rubber back, that movement of the ceramic sheds the material. Is that the thinking?
That's the thinking, yeah. So we don't go to like a full 80%, which is quite rigid. This is either what's called a single row ceramic or a double row. It's around the 40% ceramic mark. So and with a thicker rubber backing, not the 12 mil. It's typically either a 15 or a 20 mil. And hot vulcanized, not cold. Like any of these pulleys that you want that are in demanding applications and you want long service life, they have to be hot vulcanized.
And that's to do with the fatigue strength of the rubber. Is that what is the?
You get a much stronger bond with hot vulcanizing. So typically, if you take the specification for cold bond, which a lot of people use, is 9 newtons per millimeter. It's a 90-degree peel test. So that comes out of the rubber lining industry. For hot vulcanizing, you'll get in excess of 20 newtons per millimeter and what we call 100% rubber tear. So it's much more robust, particularly if you've got pulleys operating in wet conditions. When you've got wet conditions, you get the corrosion comes in from the side, and it's much easier for it to come in with cold bond. It doesn't happen with hot bulk, so it's just a more robust process.
Yeah, that's the bond of the steel to the rubber. You're saying is the water can get in when it's cold, but with the hot, it's sticky enough that the water can't get in there.
It's a full, so with the hot vulcanizing, it's a full chemical bond. You basically, the disadvantage with hot vulcanizing is the pulley has to come off the conveyor.
Yeah.
And it's put in an autoclave and it's cooked on. It's the pulley with the lagging is in the autoclave at 140 degrees centigrade and 400 kPa of pressure for 6 hours, or 3 to 6 hours. So the adhesion is, it's rubber tear. The only way you pull it off is you actually tear the rubber. Whereas with cold bond, it's a 2-part glue done at room temperature, and you can't physically get the same sort of adhesion.
Yeah, I'm just going
I will. Hopefully, this is recorded.
It's recording, so
it's recording. So I will endeavour to retrieve that file, and I will share it with you guys.
We might be able to do it from here. Let's just see if we can tag it from our end instead of setting it. See if it works. If we can click it from here, because particularly Rob, I think it's good for him to see that first half an hour. That was interesting.
What would you like to do with Brad, Kerry? Do you want to send me through an example? And then
I'll have a chat to Rob offline, because they
Yep.
did some analysis with the software of the particular conveyor I'm talking about. But I want Rob to listen to that first half an hour and then use that as a lens to see if we think we've got a problem.
Okay.
Not that I think we've got a problem, but it'd just be interesting to run some analysis on a particular conveyor we just finished, which is very highly stressed. And we just have a look at that. I just didn't think, and the feedback from the client is they got quite advanced wear on the belt. So it's a highly stressed belt, right up there on the safety factors and way past what we would recommend on safety factors. And they've got ceramic lagging on the drives. And I'm just interested to know on some of the high tension pulleys, because they'll probably be rubber back, so it won't be as scary as a ceramic backed one, but still, it's still that issue where it could start to do something with the safety factor. I don't know. I'll talk to Rob about it afterwards. Once I talk to him, once he's seen the video, we'll see if we need to chat.
Have you all got log on access to the software?
Many have, but has it all worked for everybody? Some people.
Yeah, what works for me, Kerry.
Okay, good. Yep.
So I use this software for that pulley that we were talking about here.
Yep.
Okay. If there's anybody else that you want to give access, just reach out and let me know, and I can organise it.
No, I think we're all pretty happy. Anyone ask any questions before Dave vanishes?
It's probably not the most important question, but I was just interested. You said that dragon tooth thing, that was in a copper mine. Whereabouts exactly was that in the process plant? Between what kind of equipment? Yeah.
You're talking about the one that had the dragon's teeth on it.
Yeah.
So that was the ore was a fine powder, and it had been blended with sulfuric acid, so it was like a paste.
Okay.
I don't know exactly what part of the process. I just know that it was it was the powder, and it had been blended with sulfuric acid.
Okay. So it must have been maybe in a bagging plant or something like that.
Yeah. Sorry,
That's
I
right.
don't know. Actually, Mariana would be able to tell you more details on that, because she's actually been to the site.
I'm thinking it could be Craig worked on one just recently, a heat leach system. If you got the reclaim of a heat leach system, that material's bound to have some acid with it.
That
So that could
particular
be something.
problem, that's not a once-off. That's a common problem. Like I've been into a pulley graveyard in Antofagasta, and there's heaps of pulleys there with those dragon's teeth on them.
It's
And
interesting.
you can imagine what it does to the belt.
Yeah, because there's a lot of heat leach in South America. So we're looking at one earlier. So something to think about when you're specifying equipment that interfaces with that has had acid with it. I didn't even think of that. I would have thought ceramic would be a great performer against acid, but sounds like not.
It's not so much the acid, I think, Kerry. I think there's some sort of reaction going on there where the material's binding to the ceramic.
Ah, right.
You know, there's some
rubber
sort
is
of
not
reaction to build up. So, I mean, we even looked at maybe replacing it with metal tiles instead of ceramic, but with what we've got now, the high performance rubber or polyurethane would be the best option.
Yeah, it's a good tip.
Yeah. Cool. Thanks,
All
Dan.
right.
How
Very good.
long are we? How are we going of time, Kerry?
We've got another 8 minutes if you wanted to fire up something.
Yeah, I might share screen. Maybe this was covered in the earlier meeting, but can you guys see my screen? Okay.
Yeah.
Yeah. So that for that pulley, like I said earlier, I used the online tool to do the friction analysis and the fatigue analysis. What I couldn't work out was the conveyor was designed using 0.55 as the friction factor to size the take-up. Does this graph help us determine what the friction factor we should be using? Because that's something that I couldn't work out. I was speaking to Mariana about this a couple of months ago, and she was saying that this is more for localized slit analysis. Not so much working out the friction coefficient we should be using for take-up sizing. Is that correct?
That's correct. And so in lagging select, there's we have a variable friction algorithm. So we've taken all of our laggings and with specific belt covers, Tunra has done friction testing, and we can share that friction testing with you. But basically what they've done is they've done the friction testing at a range of normal pressures from 0 up to 700. I think it's 700. What's the bottom
KPA.
there? KPA, yes. Yeah, I think it's KPA. And then they've done it also at a range of slip speeds, and you get these three-dimensional graphs of friction. So friction, did Mariana show you some friction graphs last week?
I
think she did.
I think
I can
I missed the
actually-
meeting.
Not 3D ones.
Go through the build-up of how you developed it from that press, that test rig in Tunra. So
There's the one
So-
with the zones, so your zone 1, zone 2, zone 3.
yeah. Partial
So
slip, no slip, complete slip.
That's the one. And then if you go to the next graph, if you just let me share this,
Yeah.
just let me share this, Robert.
Yep.
Hang on a sec. What's going on here?
So, David, I guess the leading question that I had was, does the online software help us determine what the friction coefficient we should be using for a particular conveyor?
Well, what the software does the answer is yes, and it does that by allowing you to develop, to put inputs in so that you eventually get no slippage. So when you get that slippage graph and the graph is saying you've got no slippage, it's basically telling you that the friction that you've got is sufficient so that there's no slippage. I'm sure there's a way of getting the actual number, but I'd have to talk to Brad about how you actually do that. Do you want the number so you can use it for other design calculations?
Yeah, for conveyor design, for take-up sizing particularly. Yeah.
So if you, Robert, if you look at this graph, right?
Yep.
I mean, I was always, when you look at SEMA, so down across the bottom here, you've got SEMA, right? So you've got the SEMA rubber one here, which is, this straight blue line, and then you've got the SEMA ceramic one above it. And it's just it's the one coefficient of friction.
It's
so it
one
doesn't
value.
matter.
Yep.
It doesn't matter what the normal pressure is, it's just the one coefficient of friction. These graphs above, these are the actual, so that those lines are for the different normal pressures, but they're done at one slip speed. If you introduce different speeds, then the graphs change. So that's when it becomes three-dimensional. So you can see the reality of friction is nothing like the fixed figures that SEMA use. Somebody obviously has done a lot of work in the past and worked out some conservative numbers that you can use and be quite safe that you're going to be able to transfer the power.
Yeah.
But the thing that, like, Euler's equation just looks at the transfer of power. It doesn't consider things like the fatigue or the slip, that affect the service life. So what we've done in lagging select, they've taken this friction, all this friction data done at different normal pressures and different slip speeds, and that's built into the algorithm so that we have a variable as you go from the contact point with T1, and you've got your highest normal pressure. As you go round the arc of contact to the exit point where you've got your T2, the friction's changing in lagging select. It's using the data from Tunra in a variable friction model. It's not using, so we don't use a single friction factor.
Mm-hmm.
And so it would be, I don't know how we would give you a just one factor to use for design.
You find a worst case?
Well,
like the worst point?
One of the developments Brad's working on is combining that transfer of power into lagging select. We don't have it in there now, but but we know that that's something that from a conveyor design point of view would be very helpful, but we don't have it at the moment.
So this 3D graph that you mentioned, David, not sure if the other guys have seen it in the earlier presentation, but does that 3D graph help us to determine what the friction we should be using for a particular conveyor?
Well, just let me find it. Just let me see if I can find one of those graphs.
Sean, have you seen the 3D graph?
I haven't seen the 3D graph, I don't think, no. But last week, I guess we asked similar questions of Mariana, and I think she was a bit more like, nah, you're supposed to design conveyors using the SEMA or DIN factors.
We're
But
only
she was
talking about the
saying-
pulley friction, right? Sorry, Kerry.
She was indicating that you could choose which mode you could have, and
Well,
it was
that
up to
was
us
the
to
issue, yeah,
determine.
on that
So there's no
graph.
recommendation, but of course we think under normal operating you should have no slip. Under normal start, you should have no slip. But then if you had something like a block chute or a flooded, you'd probably allow some slip. But she wouldn't be drawn on what we should use. She was saying, well, you need to figure that out for yourself. But the tool is there to figure it out.
I understand it now. Yeah, okay.
Yeah. I think it's like the program uses the zone 2 data.
That's correct.
Yeah, and then so it was a sort of the point was, well, if you feel like, us, like say, if we felt like we knew enough about it, could we apply zone 1 or zone 3 data to different situations?
We can share the friction data from the base testing, but I don't know that that's necessarily going to help. I think when you do your normal calculations for transfer of power and friction, are you using Euler's equation?
Only.
Yes.
Yeah.
Yeah. So at the moment, because we don't have that built into lagging select, you'd need to do that and then do the lagging select calculations and look at whether you've got any slippage or fatigue issues. And if it shows that you've got slippage and fatigue issues, then go back to the design and see if there's another way of getting the same transfer of power that would reduce the slippage and fatigue.
Yep. So Kerry, what you're saying is we want to make sure there is no slip under normal steady state operation.
Yeah.
And under abnormal operations like block shoot or even fast stopping, like just say fast operational stopping, we should assess it to see if local slip is acceptable or not.
Partial slip. So there's 3 modes.
Partial
Right?
slip. Okay.
Mariana was sort of leading to say, you could probably consider partial slip, and we know that you can't just get 0 slip all the time, from what we understood from the way the software finds it. Otherwise, it'll be too conservative. But remember, she was going to talk to Brad about doing a bit of analysis using Euler, DIN diameter, and the belt safety factors to see where that lands on that full, partial, or 0 slip graph. Actually overlay a normal design process of a belt and a pulley, because all that's locked in on the standards, right? You can figure it out. You can reverse engineer it. Say, well, if you picked a belt that was running at a certain tension, you're going to get a certain safety factor for a belt tension. DIN will then determine what the diameter of the pulley is. You pick your lagging type. So that will be known, and that means it can be transferred onto this graph to see where it would land as far as partial, full, or 0 slip. So you can reverse engineer it. You can do your selection and then put that into the software to see what's the regime. Is it safe, or do you need to move away from Euler?
I think when you talk about operating conditions and then say startup conditions or unusual conditions, the school of thought that I've heard is that you really want to try and have no slip in normal operating conditions and obviously meet your fatigue requirements. And if you happen to get, if you can tolerate a small amount of slip under startup conditions because it doesn't last for very long, and it's infrequent.
Except where you've got a monster overlaying conveyor that starts in 5 minutes.
Yep.
And the client's expecting the belt to last 20 years because it's on a soft material. So if it was an iron ore belt that flogged out, or big copper underground job that the belt's expected to last 3 to 5 years, yeah, you'd go for broke.
Yeah.
But now you got me worried about this performance when the belt gets worn. If you've gone to the limit of your safety factor and then you're running near worn, well, I guess if you've got belt monitoring, then you're trying to run the gauntlet of is the belt going to fall to bits at year 5? And by then, is it fully worn out anyway? That's what I'm trying to get my head around.
Well, that example that I showed you, Kerry, that was a mine in Peru, and that was the first high tension bend pulley we did, and we put hot vulcanized ceramic that we thought, that should be fine. This was before we didn't have lagging select or anything like that.
Yeah.
And that belt was down. It was running. The cords were running on the pulley in the center.
Yeah.
Like the lagging lasted 6 months, but it just got torn to pieces. Like it's the shear stress when you get those high. That's the reason that I showed you that stuff at the start about looking at different laggings and keeping the shear stress as low as possible, because as the belt wears, so that was a drive pulley we looked at the start. But the reality is that the stress that you're putting on, that's going to go on to the non-drives in contact with the dirty side of the belt. So if you can keep the overall stress down, you reduce the damage that happens at that part of the conveyor as well.
That's right. I understand it. You don't know that Peru belt, how old the belt was?
I don't know. I know that it was replaced. It was replaced. Not the funny thing was they had the belt and they had sections in it that were brand new, and then sections in it that were worn down to the cords. And of course, it was the difficult thing is when when you start to put all this stuff together, you see belt cleaning so important. The abrasion resistance of the covers really, really important. What you do with the lagging's important, because they all interact with each other.
And if everything's on the limit, this is what's got my interest now. If everything is on the limit, you really haven't got any kind of leeway for when the belt gets worn. So when the belt gets worn, all these factors are now past critical.
And you're just chasing your tail, like the maintenance guys are just chasing their tail. There's nothing you can do.
Yeah. Yeah. Interesting. Yeah, the new thing to consider.
Sorry, just one more question if we have time. David, are you familiar with several years ago that I think it's Brett DeVries that wrote this paper. Basically, he's done a similar thing where you consider the normal pressure. It moves away from DIN 22101 and just choosing a number for the friction coefficient. I'm just trying to find the paper.
I can send it to you. I've got the paper.
Well.
Yeah, I've got the paper. So
is your software sort of based on that paper or?
So that paper. So if you look at the paper and you look at the way that DeVries tested, the way that he tested friction, it's pretty much the same as what we've done at Tunra. We looked at that paper, and then we discussed with the Tunra guys how we would do the test, and it's very, very similar.
Right.
So what the DeVries side of things does is it's looking at slippage and localized slips. So it's looking at the first. Yeah. It's looking at the first. What's the first graph in lagging select? The fatigue thing that's in that second graph. That's like a completely separate. The way that fatigue one came about was we provided the CAD models of all of our lagging to Conveyor Dynamics. We then provided all of the dynamic physical properties of the rubber, things like Poisson's ratio, Young's modulus, the shear crack resistance, I mean, just all the physical characteristics. And then that was put through an FEA analysis to determine the fatigue life. And we arbitrarily picked 5 years, and we arbitrarily picked a certain number of cycles. So when you look at that graph and you get a red zone and a green zone, it's based around just an arbitrary number of 5 years. And it's really just to show, it's just for a comparison, you know, between something that should last 5 years and something that likely won't.
Yep. Okay. Yeah. But I think this paper came out maybe 10 years ago, but I don't know. I just found it bizarre that, you know, the friction coefficient is more than 1 under lower normal pressures, but you can see there it's more than 1 there, more than 1 there, and yeah.
We got the same results. I can share the 3-dimensional figures with you with different. So what he's done is normal pressure. What we added, we also added in different slip speeds.
Yeah,
and at one point on a lot of the laggings, you actually get friction at low pressures up to 1.4.
1.4. Okay.
It's when you get into the higher
Right.
normal pressures that it comes down and it gets much closer to the SEMA figures.
Yeah. Okay. No, it would be good if you can share the information.
Yeah, I can do
if it's
that.
okay. Yeah.
There's actually a presentation that Peter Robinson from Tunra did on the friction. It's a video and a PowerPoint. I can send you a link to that if you'd like to have a look at that.
Yes, please.
Okay. Have I got your email, Robert?
No, but I can flick you an email, or if you send it to, I don't know who organised the meeting. Was it you, Matt?
I can send it to Sean.
Yeah, if you send it to
Yeah.
Sean or Matt or whoever,
Yeah. Okay.
they can pass it
Can
on
you
to
send
me.
it to me as well, please? I'd be interested in seeing it.
Who was that?
Matt.
Matt, cool.
Yeah, Matthew. Yep. Okay.
Yeah.
Okay. No problem.
Cool.
Easily done.
No worries. Anyone else got questions? I suppose I'm good.
It was very interesting. Thank you so much.
Thanst for your time,
Yeah, it's
guys.
awesome.
Appreciate it. It's like a can of worms, this thing. We've actually just so you know, we just found out yesterday. We put in for a government grant in conjunction with the University of Newcastle, because a lot of this work was funded through a linkage connection grant, and we've just got another grant from them. And what we're going to do now is all of that friction information. We've got money. We're going to buy a machine for doing the friction analysis at different temperatures. So we're going to go minus 40 degrees C and then up to 70 degrees C. So we'll do all the friction plots at those temperatures, and then we'll load that into Lagging Select, so that if you're, for example, you're designing a conveyor for Mongolia, and it's, you know, in the winter it's minus 40, you'll actually be able to look and see, because the friction is completely different at those temperatures. And then the other thing that's we've got funding for is we're going to do fatigue analysis for the different bonding systems. So cold bond, hot bulk, direct bond, and then the tile bonding. We're going to be able to do that at the different temperatures as well. So we'll be able to put that fatigue life for the different bonding systems in at different temperatures. I mean, that's going to take 2 or 3 years, but
Looking forward to it.
yeah, but we'll keep you
Stay tuned.
updated.
Yep. Cool.
Thank you very much, guys.
Thank you so much. Thank you.
Yeah, thanks for that.
You'll have to
See you,
text
Robert.
me
See
the
you,
results,
Andrew.
Matt.
See you, Sean.
I don't think.
See you,
Thank you.
Matthew. See you, Kerry.
All right, cheers.
Thanks a lot. Bye-bye.
Bye.